Hello, everyone. Good, good to see you during the Easter week, which is. Hope you enjoyed the sunshine. So we're waiting for David. David is going to join us, and we'll start the webinar. If you have any questions for me, feel free to ask. David is here. Have you all read the assignment? Have you all opened the assignment on logs and exponents? Hello, David.
Hi, Vlad. How are you?
Hello, good. Are you in collaboration with NASA?
Yeah. I'm joining from outer space.
Cool. Right. Okay.
Super. Just to let you know, I've been having problems with my Wi-Fi on and off today, so it seems to be working at the moment, but it's been a little bit patchy. I think there's been a nationwide problem with Virgin Media.
Yeah, there's lots of issues currently.
Cool. So have people all looked at the sheet already?
Yeah, they're saying yes, mostly.
Excellent.
Yeah, I'd say 95% yes.
Okay, if people could put in the chat particular questions that they would like to look at from the sheet, then I can take some requests. I've looked through the sheets and I've found some questions which I quite like as well. And then we can play a little bit by ear. Just looking in the chat now. Okay, so people have looked at the sheet. Right, I'm going to share my screen. Oh, wait a minute. Sorry, I'm just going to stop this share. No. Okay, I'm going to share my screen. Okay, so here's the logarithm sheet. I'm going to start with a question which isn't on the sheet, but one which I really quite like. Because it's a proof that is quite a nice. It's a little bit of number theory, which one doesn't often meet, and it's quite a nice exercise in proof. So the exercise is this. So question. Prove that log base 2 of 3 is an irrational number. Now, I'm a pure mathematician at heart, so this is quite a nice exercise in pure mathematics. So it's a good example of how to lay out a proof. It's also quite a good exercise involving logs. So let's run through this let's run through this proof. Proving that something is irrational is the same as proving that it's impossible to be written as a fraction. And this is a good sort of tip, that any impossibility proof is almost always best done as a proof by contradiction. So let us assume for contradiction that log base 2 of 3 is rational. So what does that mean? That means log base 2 of 3 is equal to n over m. And in terms of writing style, and this will be very important for admissions tests and also when you get to university, we should say what we mean by n and m. So n is, well, n and m are natural numbers and m is not 0. Okay, because we can't divide by 0. Okay, so what does log base 2 of 3 is equal to n over m? How else could we write that? Well, this is where it's a good exercise in logs. So at least in your own mind, think about how we can recast this statement about logarithms in terms of a statement about powers. So if log base 2 of 3 is equal to n over m, that's the equivalent saying that 2 to the power of n over m is equal to 3. Now, if we remember our laws of indices, this fractional power of n over m is the same as the saying that the mth root of 2 over n is equal to 3. And if we raise both sides to the power of m, we get that 2 to the power n is equal to 3 to the power m. Now, what we want to do at this point is we want to show that this is impossible. So why does this lead to contradiction? Why can't 2 to the power n equal 3 to the power m? Now, obviously, if n and m are real, then that's possible. But we've restricted to whole numbers. Now, if we restrict to whole numbers, then 2 to the power n is the sequence. Well, there's no reason why n can't be 0 at the moment. We haven't shown that it's not. So the sequence 2 to the power n is 1, 2, 4, 8, 16, 32. The sequence 3 to the power m, remember can't be 0, is 3, 9, 27, 81, 243. So what we're looking for is we're looking for a reason why no number can be in both lists. Okay, because if there was such an n and m, then 2 to the power n would be equal to 3 to the power m. So we'd have some number which was in both lists. Well, I think we can all see why this is going to lead to contradiction. 3 to the power m is odd for all m in the natural numbers. Okay, just to check if people are still watching, if people are still alert. What would be the best method of proof to show that 3 to the power m is always odd? In the chat, yeah, induction. Okay, now this is actually such a good example of induction that even if you've not heard this word before, this is a good idea for the inductive, for the whole notion of what a proof by induction is. So if we think about the sequence 3 to the power m, it starts off at odd. So 3 to the power 1 is odd. And then if 3 to the power k is odd, 3 to the power k plus 1 is also odd. as the product of two odd numbers that being 3 and 3 to the k, is also odd. So the idea is that this sequence 3 to the power m starts odd. Each step along the way, we're multiplying by 3, which is an odd number, so it remains odd. We never pick up an even factor. So 3 to the power m is odd for all m in n. However, 2 to the n is even for all n greater than or equal to 1. So therefore, if 2 to the n is equal to 3 to the m, then 2 to the n is odd, as 3 to the m is odd, which implies that n is equal to 0. Okay, because so the argument there is that the only odd number in the list of powers of 2 is 1. Okay, everything else is even, and all of the powers of 3 are even. But this is going to lead to contradiction. But if n is equal to 0, we have log base 2 of 3 is equal to 0, which is clearly false. Because 2 to the power 0 is equal to 1, which is not equal to 3. So we've reached our contradiction. Okay, slightly more sophisticated argument could have just appealed to the uniqueness of prime factorization. Every natural number has a unique factorization of primes. So there's no natural number whose prime factorizations on the one hand could just consist of 2s, but then on the other hand could just consist of 3s. Okay, so where things fall down at this initial assumption that log 2, 3 is rational. Okay, so therefore we can conclude that log 2, 3 is irrational. And hopefully, you can see that log 2, 5 is irrational, log 3, 7 is irrational, and I'll leave it to you, and I think this would be a very, very good exercise in pure mathematics, to try and generalize this result as much as possible. So if a and b are whole numbers, when is log AB rational? Okay, nice little warm-up example. Does anybody have any questions about that example? If not, put a thumbs up in the chat. Also, put in the chat any requests from, if there's any questions on the sheet which you would definitely like me to go over. Okay, we've got a thumbs up from that first proof. I hope people liked that. Nice little bit of pure mathematics. Okay, let's have a look at some of the problems. I'm going to look at problem number 2. So it says, given that y is log base 8 of 3, find in terms of y log base 3 of 8. Okay, so let's do this. Let's do this lots and lots of different ways. Okay, just to give you and then log base 9 of 2, just to give you lots of different approaches to looking at logarithms. So one approach of working with logarithms that always works is, if you feel uncomfortable with logarithms, to turn stuff back and look at powers. Okay, so if log base 8 of 3 is equal to y, a completely equivalent way of writing this is that 8 to the power y is equal to 3. Okay, these two things are just, these two statements are just complete synonyms of one another. Now, in order to find an expression for log base 3 of 8, we're looking for an expression saying 8 is 3 to the power of something. But there's something that one can do between these two lines, is that we can raise both sides to the power of 1 over y. So if we say, if we take a power of 1 over y to both sides, then 8 to the y to the power of 1 over y is the same as 3 to the power of 1 over y. But our law of indices says that 8 to the power of y times 1 over y, we just multiply the by the powers, so we just get 8. So we can write 8 is 3 to the power of 1 over y. Okay, and now we're 100% done, because if we just write this in terms of what logarithms mean, log base 3 of 8 is exactly this exponent here, 1 over y. So the answer to part I is 1 over y. Okay, so this is method 1. Method 2, okay, is also worth, well, it's something which I'm pretty sure that you already know, because it's very worth knowing, is that really we can get away with not using this rather esoteric base of 8. Okay, you know that in mathematics, you know, on your calculator, well, for a long time through the history of mankind, people sort of just use log base 10, and then once you get to calculus, people just use natural log of e. And you probably know that your calculator just has a natural log button. We don't need a button. Well, actually, the more modern calculators do have a button where you can specify the base, but we can get around that. Now, why? Because there's a change of basis formula. So let's generalize the method that we did before. So let's say we've got log base a of b is equal to x. Again, just by thinking of what logarithms are, we know that that means that a to the power x is equal to b. And now if we just pick our favorite logarithm, yeah, our favorite basis. So let's do natural logarithms. The natural logarithm of a to the x is the same as the natural logarithm of a to the b. something to put into the chat at this point is, and this is the sort of thing which in your written work you should really try and include, what property of the logarithm justifies this if and only if symbol here? Why is a to the power x equal to b equivalent to saying that the natural logarithm of a to the x is equal to the natural logarithm of b? In particular, why is that reverse implication true? Let's see. In the chat, yeah, good. Okay. Someone's put in the chat that the reverse implication is true because log is a one-to-one function. Okay, because the natural logarithm is a strictly increasing function, okay, there is only one value that attains where the natural logarithm attains the value of a given value. Sorry, Wi-Fi blip number one. Oops. I just need to wait for Vlad to make me host again. No, I'm just gonna. I just need the text bar. Sorry about this. I was just in the process of proving the change of basis formula. I've just sent Vlad a text. So I'd got as far as saying that we could log both sides of a to the x equals b. So we've got log of a to the x equals log of b. And then we can use that law of logarithms to pull out the x. And that will get me the rule that x is log b over log a. Just waiting for that. Sorry about this. Hi Vlad, sorry, my Wi-Fi dropped. Can you make me host again? Thank you. Okay, I've got through to Vlad.